A very good afternoon to everyone. I'm Adya Shakti, your host for the day. I welcome you back to the 3-day national webinar on lithium-ion batteries and beyond, a perspective for future energy storage need. I hope everyone has enjoyed the first two talks of session 1. Now we are back with our session 2 of day 3. We have with us Professor Pritam Singh from Ceramic Department, IIT PHU, to deliver his talk. Please kindly to put up your questions in the comment section. At the end of the talk, we'll be able to take up few questions. Now I kindly request Professor Ranaprata Majumdar to come to the podium and introduce Professor Pritam Singh to our audience.
Good afternoon, all of you. It's my great pleasure to introduce Professor Pritam Singh. He did his MS PhD from Solid State Structural Chemistry Unit of Indian Institute Science, Bangalore. And after that, he did his postdoctoral research in Mechanical Engineering, Texas Material Institute, University of Texas, Austin, with pioneer of rechargeable lithium-ion batteries, Professor J.V. Goodenough, that is, that Nobel laureate professor. And he has several publications in international journals, and he is among the top 2% material scientists in energy materials section in world by Stanford University. His research areas are renewable energy, reversible alkali ion, lithium sodium batteries, pseudo-capacitor and hybrid supercapacitor, solid oxide fuel cell, OER catalyst, water gas shift catalyst, sensor, and high-K dielectric materials. With this short introduction, I am requesting Professor Pritam Singh to start his presentation.
Excuse me, sir. Sorry for the interruption. Your voice is not audible. Excuse me, sir. Sorry for the interruption. Your voice is not. No, sir. Your voice is not audible. Sir, I request you to rejoin in the session. Hello, sir. Hello. Hello. No, sir. You're not audible.
So now I'm audible?
Yes, sir, you're audible now.
Okay, okay, great.
Okay.
So let me share the slide. So do they allow only PDF file in this one or PPTs are allowed?
PPTs are allowed, sir.
Okay, PPTs are allowed, no? Okay. But PPTs are not coming. That's what I'm seeing. Let me see just 1 minute. Desktop, I'm giving talk today. I'm trying to share the slides. Or okay, share screen. Sharing screen is easier with two. So now it's the visual. My slide is visible. Hello, Uday. My slide is visible.
Yes, sir, your slides are visible now.
Okay,
Can you
great.
please make it a
Okay.
slideshow?
That I think I made into the slideshow only. Now it's changing or it's showing one by one slide.
No, sir, it's not changing.
Okay, it's not in just 1 minute. Let it be. Okay, so let me first open it here. So just 1 minute. I'm uploading because that's why it's creating problem. They need the uploading, I think. Yeah, now you have the slide. Yes.
Yes, sir,
So
we have the
yeah,
slides now.
yes,
Can you please
yeah,
move the slides to make it confirm that it doesn't cause any interruption in between?
yeah. Now you can see the slide
Yes,
is
sir, your
changing.
slides are moving. Yes, sir, perfect.
Yeah, yeah. Thanks.
Thank you, sir.
So, Professor Majumdar, thanks. Sorry for the interruption. So, the topic of my talk is transition metal oxalate based supercapacitors. So, as this topic is actually the conference is on the lithium ion battery, but the world is moving towards the lithium ion batteries and upgradation of the lithium batteries. So, what is next into that one? So, just a general brief introduction about my laboratory or what I'm working. So see here I'm in IIT BHU RRC as the already my topics have been introduced. So here I'm working on both domain of the energy generation as well as the energy storage. See, all the generation side, I'm working on the solid oxide fuel cells or ceramic cells, and then I'm also working on the energy storage materials, especially beyond the lithium-ion batteries. So more on the sodium-ion batteries and the pseudo capacitors or the super capacitors are a key for the generating the large-scale energy storage, which are the current research topics are what we are really needing of. So see, if you see our current challenges, the major challenge the world is facing that we want to go on the renewable. And if we go on the renewable, the solar power is only available for the 8 hour in a day, and wind power is not at all that giving the fixed power and all at any time. So see, energy storage is one of the key challenge we are facing in 21st century, and that's why we need a bulk storage. It's a time to move on beyond the storage properties or storage solution for the EVs or for the this batteries for automobile, this our cell phone and laptops. So see, beyond the portable electronics, there is a need for a heavy energy storage or bulk energy storage devices then only we can able to use the full potential of the renewable energy. Otherwise, see, we can use only the amount of the grid loss is there. See, currently the total solar and wind network in Indian grid is close to 3.5%, and our grid fluctuation itself is around 5 to 7%. So that's why without even using battery, we able to use the solar energy or the wind energy what we are generating in India through the grids. But if they will go beyond the fluctuation limit, then there will be a heavy chances of the grid damage if we are using these energies, and there will be suddenly loss and gain of the power or very heavy power fluctuation. So to avoid that, we need the bulk storage or the bulk energy storage. Okay. So if you see the storage technology, there are the three kind of technology which we generally know. See, one technology comes as a very, very mature way in terms of lithium-ion batteries, which is actually devising our portable electronics. Now, even going much longer from them, and we are entering into the EV section using the lithium-ion battery. The another things which we know very well is the EDLC capacitors or the double layer capacitors. These double layer capacitors are just like a power booster, and mostly they are utilizing as a spark plug to ignite either the rockets or to just give the high power solution for a few seconds or the milliseconds. However, there is a need that if you want to have a grid scale energy solution, not only the energy density has to be increased of the battery, but more is the charging and discharging rate. Or in a way, we can say that the power must be increased of the battery. The power to increase the power density or the charge rates. So now world is moving on a coupling of the devices, which will be intermediate of the battery or the capacitor. And owing to that things, the world is moving towards the pseudo capacitors. Means the material which can behave both like a capacitor as well as like a battery. So we have a high power as well as a high energy density together. So that's what is the talk of the today, or the talk of the future, where people are going, and the world is moving very extensively on either the redox flow batteries or the aqueous capacitors for doing these things. So as we know about the lithium-ion batteries, I work with the pioneer of the lithium-ion battery, Professor John B. Goodenough, and he set a certain concept in the batteries, especially using the non-aqueous electrolyte, when you can increase the energy density of the battery by increasing the applied voltage. It's not that the batteries were not before. See, Professor Goodenough Whittingham has already stabilized the titanium sulfide-based batteries, but due to the sulfide metal, the voltage window was little lower or close to 2 volt. However, applying lithium cobalt oxide as a cathode material ranges the battery voltage above 3, and that has increased the certain component of the energy density as well as the power fluctuation. That's why these batteries come up to the commercialization. So there are the certain things involved. See, we have to always see that how much it can go up to the energy density wise, and that's why when it comes to the safe battery, Professor Goodenough has invented another material called the olivine based lithium iron phosphate. So see, in the battery domain, the most of the work was happening in the principle of redox chemistry as well as the intercalation of cations. So redox chemistry means active ions like cobalt or iron. So they can be involved. So like in the lithium cobalt oxide, cobalt 3 can be oxidized to cobalt 4 plus, and this way lithium can be leached out from the material, and then it can go through the electrolyte into the carbon anode or the graphitic anode. And when we do the energy harvesting, that time during the discharge process, the electron will regenerate, cobalt will reduce again to 3 plus, and lithium will again intercalate into the cobalt oxide matrix, and in a way you will get a lithium ion battery, working lithium ion battery. So see, the battery concept was very important. That intercalation was very important to get a robust performance or the reversible performance when the electrode degradation will be very low. So that's why one of the key criteria what people are looking in the capacitor, that can they get the intercalative kind of storage along with the surface storage. So this is the way we can get the dual generation. So, and when you see the current battery status, there are the battery limitations. Using the Regane plant, you can usually say that when specific power increases, the energy density of the battery decreases. So we have to make a trade-off on making up a battery for the particular application. So it's always a trade-off that you want a high power or you want a high energy. And in between, we try to make a path of getting both together in a certain extent. And that's what the research all about is. So then, so what are the major problem? The major problem currently we are facing, if you want to get a grid storage, then we need a maximum power capabilities and along with the maximum energy storage capabilities. So see, those two powers has to be merged together. So intensive work is needed on the charging and discharging parameter that has to go up. And in many times we need the instant response when we actually want to save the grid from the failure. So these are the major problem where world is looking, and depending on that, new energy solutions we are focusing. So, and then why this grid scale energy storage is very important, because if you see the total energy domain where the energy generation and storage is there, if you see our residential, commercial and non-electric usage less than 11% of the total energy, means this is the total section of the cell phone and laptops. The industrial non-electric section is 22%, means a completely coal and fired based, gas fired based, combustion based system. So there you don't need the energy storage. But if you see the transport section, where into the EVs you are looking for the electric solutions, battery solutions, and then you are looking at electric grid side solution, because that's the 39% of the total electricity usage. So, and that's why we need to be focused on the grid scale energy storage solutions, because they actually hold the potential for the continuous power supply to the mankind, especially the country like India, where we have very heavy line losses and very high burden is there on the electricity resources. So what we are trying to do a coupling of a energy density as well as energy power, high power together. So if we able to do this ultra capacitor storage, I mean, and the battery interconnection together, we may come up with the better material or the better device which can have a potential to go into the grid scale energy storage, even can be replace the lead acid inverters in the country, because these are the another very important aspects. See, here in India power losses are very heavy, and due to this there is a power cut, and then we have a heavy usage of inverters in our houses. And what we use for the inverters? Lead acid batteries, because lithium ion batteries are very costly, and then the even power performance of the lithium ion battery is not up to the mark. So the aqueous acid based lead acid batteries are working, but lead acid batteries are very toxic. So when if you see the India perspective, we need to omit the lead acid battery. So even for that, these hybrid capacitors can be a very potent solution. So, and that's what India is realizing. See, currently it's the momentum shift time into the batteries research. See, even if you see the whole world, already the lithium technology is much more mature. Whole lithium resources in the world is in the China. So even if India want to do much on the lithium ion batteries, it is actually of no use, because whatever you do, you are not going to decrease the processing or the making cost of the lithium ion batteries using the lithium from the abroad or from the China control. So that's why we have to work on the more new technologies where still the whole world is on the baby step. So if we take any lead at that stage, that can benefit us in the long run. And that's why electrochemical hybrid supercapacitor and metal ion capacitors become a new focus, especially for the EVs and also for the grid scale storage. So that's what we have to see. If India is really looking to become a superpower or a global power in energy storage, we have to think beyond lithium ion batteries, because if whatever you do the lithium ion batteries, we actually lost the race. We cannot do in that term in too much. So that's why this our focus, especially in my laboratory, is working on the electrochemical capacitors using the sodium ion intercalation, or as well as the aqueous capacitors. So if you see the supercapacitor, so supercapacitor are the what we want to make really is, can we replace the EDLC electrode with the pseudocapacitor electrodes? So that's the total is. See, one side the activated carbon or EDLC kind of electrode can be there, which can do the very fast charging discharging, as well as the pseudocapacitor electrode can increase the intercalative storage. So in that way, we can increase the energy density of the capacitor, and the power density will come through the capacitor type nature of the storage. So that's why the dual intercalation can give you the high energy and high power solutions. So then once we're able to get it, then we will have a very potent application in EVs, as well as we will get into the grid storage. See, and more important, we'll able to replace the toxic lead acid inverters from the households. That's the major things what we are looking. So see, for that the world is hosting, and the world is going about the search of the new materials. One of the my focus in the research was always on the development of the new materials. And what I found that the framework materials have a still heavy potential to be utilized as a cathodes or anodes into the batteries, as well as positive and negative electrode into the pseudo capacitor or the hybrid supercapacitor. See, in the capacitor there is no positive or negative electrode when you go for the EDLC type of. But when we are coming about the pseudo capacitor or the battery kind of capacitor, then surely there is the voltage gap, there is the voltage window, and then the whole lot concept of the batteries are going to be utilized into the capacitor section. So here again the capacitor electrode will be positive and negative depending on their redox potential. So when you are using the carbon based, they will be called as a negative electrode, and then the metal ion, which will have a certain higher redox potential, they will consider as a positive side of the electrode. So why this oxalate framework? Oxalate framework is actually very unique. See, oxalate based materials are easy to synthesize, more easily available, and then see oxalate which thinks it's as a planar molecule, but actually it is not. Oxalate can even rotate, and it's both carboxylate can be perpendicular to each other. So even if it's a hydrated oxalate, then it will be surely a three-dimensional structure. But even non-hydrated oxalate can also form a three-dimensional structure due to rotation of their oxalate linkage. Okay, so this CC bond is actually rotatable, so you will get both oxygen perpendicular to each other. And that's what we have seen, that even this after removing the water, we can get a much higher three-dimensional structure to get a high energy storage. So the work we have actually started with the nickel oxalate nanoflex. See, that's why what I was telling, that see, initially we started with the hydrated oxalate because we thought that the hydrogen bonding or the channels from the water will make the three-dimensional architecture of the nickel oxalate that will help to get a better intercalation of the ions or the better diffusion of the ions, to get a dual storage, not only the surface storage as well as the bulk storage also. And can we get something like that? So see, we have done this test in aqueous electrolyte, aqueous KH electrolyte, and what we have found, that you can see this the cyclic voltammeter and the voltammetry, and this is the nature of the CV. If it's a capacitance, pure capacitor, it will be like a rectangular. If it's like a intermediate capacitor or the pseudo capacitor kind, then you get a distorted rectangular. But what you are seeing is a completely a peak. Charge peak and discharge peak are completely a intercalative nature of the behavior. And that was very, very surprising for us. Means actually the hydroxide ions, when nickel is getting oxidized, hydroxide ion is actually intercalating through the 3D structure of the nickel oxalate, hydrated nickel oxalate framework. And even we have seen that with the high current rates and all, there is not much change into the shape of the peaks, and there is a linear shift with the increasing current rate. which actually suggests that the behavior is actually type of intercalative. And then even we did this galvanistic charge discharge study, then also you can see the stable plateau. See, we are in the aqueous electrolyte, that's why this redox potential are really low, and for the single cell. So when we have gone for this nickel cell, you can see this discharge and charge potentials are there, and you can get a fixed storage. And see, we are getting at much higher current, again up to 5 ampere per gram current rate we able to do this intercalation, the intercalation. Okay. And the specific capacitance extension was very high. So what we thought, see, because see, nickel oxalate single electrode had shown a much intercalative kind of property. So as I told that, see, now we want to mix, we make a composite or a hybrid supercapacitor. So we have taken activated carbon, which work like EDLC electrode, into the high surface, due to high surface area, high storage you can get in activated carbon with the very much like a capacitor performance. And then when we have taken activated carbon as a counter electrode or negative electrode and nickel oxalate as a positive electrode, we have done the cyclic voltammetry or charge disappearance. Now you cannot see the distinct redox peak. However, we still can get a very high energy and high power together. So that's why there is a redox voltage coming around above 1 volt during the charge and around 0.7 volt during the discharge. So we able to get a moderate high energy and high capacitance performance, and around that 2 ampere 0.2 ampere per gram current density, the energy was close to 140 watt hour per kg, and the power was close to 800 watt per kg. And if you go to the 2 ampere per gram, which is a very high current rate, then also we can get around 6 watt hour per kg energy density, and around more than 5500 watt hour per kg the energy density. So see, nickel oxalate, hydrated nickel oxalate gave us a momentum that, see, these 3D structure can be activated and can be involved into the dual cell to release the high energy density, and we can work in the direction of making hybrid supercapacitors using these oxalate frameworks. So then further we extended our work on the cobalt oxalate. See, we started with the cobalt hydrated oxalate, then we have done the complete water removing step, and the material has been converted into the cobalt oxalate nanorods. They are not that the nanorods of the few nanometers, but they are close to the 150 nanometer in the depth and around 1000 nanometer in terms of length. So they are actually very bulk rods. They are not exactly into the very nano, but it's into the sub nano region or the micrometer region. So when we have done, see, now you see this, when we have a cobalt oxalate hydrate, then it was a more surface redox behavior and dominated with the surface intercalation. However, when we remove this water, we can get a much intercalative. So see, due to removal of the water, much porous structure has been created inside the nanorods or inside the rod, which actually led to the diffusion of the hydroxide ion into the much larger extent. And that's why we get a much higher even the energy storage if you see the total area under the cyclic voltammetric curve under the same current rate. So this is the direct difference we got. And see, when you increase the intercalative nature, actually the surface storage remain there because it depends on the surface area. So overall you come up with a dual performance. Yes. So then we have done this charge discharge. So if you see the cobalt oxalate hydrated, this total time is around 600 seconds. However, the same anhydrated material, the charge discharge has gone up to more than 2200 seconds. If you see this timing, and if it is a half ampere per gram current rate, very good current rate. So even if you see the total charge time, it is close to 1000 seconds. If you convert that, means we are close to 15 minutes to 16 minute charge discharge. So now this capacitor is actually holding the charge for much higher time, from few minutes, seconds to it's gone into the few minutes. So means we can get into the battery type of performance into the capacitors with releasing much higher energy density. So even if you see into the 1 ampere current density, we can hold the charge up to 500 seconds or more than 8 to 9 minutes. So in that one, the capacitance is close to 2200 farad. And if you see the energy density at 1 ampere, this one, it will be close to 120 to 130 milliampere hour per gram. So we are reaching up to that extent using this cobalt oxalate and cobalt oxalate, these nanorods. And then we have done into the full cell performances. See, now in the full cell, we can get a much higher this plateau. So then we are actually tending more towards the battery type of behavior, even though we are using the capacitor kind of counter electrode. So the power density, and if you remember, see now our power density has increased up to 4 kilowatt hour per kg into 3 ampere per gram, and the energy density is also close to 90 watt hour per kg, and it is now much better than the lead acid battery. Even when we have done this with the cobalt oxalate. So see now that significant change is happening with the oxalate framework. So this is actually coming as a new structure family where lot can be done by tuning of the active redox ion and using the oxalate framework. Further, we have extended our work and we have made the doped material, means cobalt and nickel both we have intercalated together, even though nickel uh, has shown the little lower performance, but nickel has shown very high intercalative. So when we have made this together, you can see from this CV, compared to hydrated one, the non-hydrated is actually performing much better because much porous structure is actually created using this anhydrated oxalate. And the redox peak is completely intercalative. And the if you see this the flat part, which is more like a capacitor plot, it is also much higher than the hydrated one. So these are the surface morphology. So we have more like a flux, means a powderous material, but it is more fluffy material. That's what we can say when we have doped this material, we have found it. There is no special structure, but fluffiness is there, more porous structure is there. And then we have done the actually full cell test using the cobalt and nickel, this one, this one. And then what we are find, even up to 10 ampere hour per current we can charge it. So see now the charge and discharge can do at the much higher current rate, and even at the 10 ampere per hour current rate we are getting close to 70 watt hour per kg energy density. If we compare with the cobalt oxalate, when 5 ampere current density, now we can get even the 150 watt per hour and around 3 kilowatt hour per kg into the term of the power density. So see, this framework have been increasing continuously. However, there are the more challenges are there when we will go actually for the devising. Even the aqueous KOH electrolyte, people are looking to go on the more neutral electrolyte like sodium sulfate or the potassium sulfate to remove the corrosive nature of the hydroxide. So there are the many future study. But see, now we have want to also extend our work on the activated carbon side, because can we get a more intercalative electrode than the carbon, and with reaching almost the same capacitance performance, then the better intercalative kind of intercalative battery type capacitor can be developed. So see, if we just see into the cathodic side of the changes and the cell performance, see the energy density of the lead acid battery is typically in terms of 35 to 40 watt hour per kg, and the power density is close to 180 watt per kg. And see, this power density or this is looking very low for lead acid battery, but we should not forget the high weight of the lithium is involved in the means lead is involved in that one. So that's why see the kinetics of the lead acid batteries are really good. There is no doubt in that one. And the same way lithium-ion batteries are close to 100 to 250 watt hour per kg, and even energy density is 250 watt to 340 watt hour per kg. So at a higher current rate, uh, we can even reach to see when we go for the battery kind of current like 1 ampere per hour, the cobalt nickel oxalate can generate even 870 watt hour per kg, and the energy density also close to the mean the power density is also even close to the in the range of the lithium ion batteries for the cobalt nickel cell. So see, cobalt. So these object-based framework materials have been coming into the light to make the better or the new energy storage systems with the much higher charge discharge performances. Okay. So now I will just going to share about the our other another research which we are actually doing on the anodic side or the carbon side. So recently we have developed the another intercalatory pseudo capacitive electrode, and that is happening into the negative voltage. Okay, because see here we are using the iron 4 plus redox couple. So it's inherently what we have seen if you see this LaKFeO3 or LaFeO3 doped with the potassium, the structure is gone into the orthorhombic, and very much like alternative lanthanum and potassium has been there. So this lanthanum and oxygen polyhedra can make a negative and the positive charge over the redox, and that's they can elongate the octahedra. So this elongation or this dipole will make the orthorhombic cell or the distorted octahedra. What we have found advantage of this leads to the oxidation of iron to iron 4 plus. So instead of only doing iron 3 2 couple, we able to actually get iron 4 to iron 3 and iron 3 to 2. So do a two electron exchange is possible, and that's what we have shown into this work. So this is the general doping pattern. We have able to make it even up to 50-50. So La 0.5 K 0.5 FeO3 minus delta have been made, and delta is actually close to 0.11. So almost oxygen stoichiometry is close to 2.9, 2.8. So then these are the bulk materials. Very regular powders arrangement we have gone into this one, like a ceramic powders it used to be, and you can see that for the 50-50 composition we get a highest capacitance, and in the cyclic voltammeter you can see there is a clearly two redox potentials are there. So one is for the iron 3-2 couple, and one is for the iron 4-3 redox couple, similarly into the charge cycle as well as into the discharge. So see, during this doing this the alternate lithium and this potassium this alternate into the iron octahedra, we able to tune actually the redox chemistry of the iron and able to get the dual iron exchange. So then we have studied the charge storage mechanism, because see, most of the perovskite people talk about the oxygen intercalative storage. However, it is not at all to have a oxygen intercalation into the material if you don't have a very high oxygen vacancies. See, no, there cannot be a oxygen excess perovskite. See, oxygen excess perovskite is a myth. Actually, it's always a cation shortage this operator, because see the whole network of a cell of a crystal is actually a anion supported cell. So if you make a LaFeO3 and you tell oxygen extra, so where this extra oxygen is going to incorporate? So it's not possible to incorporate extra oxygen into the lanthanum oxide a perovskite structure. However, you can tell it if you have a cation shortage. So then see, when we have done our charge discharge, this is the energy storage used to be very high. See, the diffusive type of storage itself is only 30%, but the capacity is close to 70%. So what we have found in the mechanism, actually this perovskite material, there is a interconversion is happening very heavily than the intercalation or an excess. So oxygen actually get reduced to hydroxide ion, And this is the way iron 3 actually get reduced, iron 4 and iron 3 get reduced to iron 2, and we get such a high energy storage. So even using the lanthanum, this FeO3 cell, we can get this storage. So see, interconversion is a very much favorable mechanism into the perovskite materials. That's what we have found, and now a lot of work is going in that direction to make a alternative of activated carbon, because lot of work is going on the active transition metals ion pseudo capacitors, electrodes. So this combination of these two can result us as a battery kind of aqueous battery kind of material, and means battery kind of storage, and we may able to generate the very high charge storage and the power capability using the cell made of the oxalate cations and the LaFeO3 based anions. You can see here the charge discharge is the time gap is close to this one. At the 1 ampere gram is up to 1300 seconds. So up to 10 minutes it's getting the charge, and almost 10 minutes it's getting discharge at such a high current. And the capacitance is also close to 600 Faraday per gram. Even at the this one low current, and this 152 at 10 ampere per gram capacitance is close to 75. So see, this material have a potential to go beyond that one, and can give us the much higher performance to be seen as a new kind of this battery type capacitor materials. So with this, I would like to thank you for listening me, and the talk is now open to take the call for the audience. So I will be very happy to answer your questions.
Thank you, sir. We have few interesting questions from our audience, which will be displayed on your
Okay.
screen.
Sure. If hydroxide formation play a significant role in the performance of oxalate, then how do you compare metal hydroxide, metal oxalate? Yeah, it's a really nice question. And what is the part two? Okay, so see, this is not please on the advantage of metal oxide and hydroxide. Okay, that's very important. See, when you have a metal hydroxide, like a nickel hydroxide or the oxy hydroxide, NiOH has been already proposed. See, major problem of these hydroxides in the higher pH, they go into the degradation. So instead of hydroxide, they will go around the nickel oxide formation, or even the oxide nickel oxidation into the nickel 3 plus, and you will get a black color compound getting separated out. So that's why when you have a framework structure, that gives you the extra stability. So here we are not getting the conversion of nickel oxalate into the nickel hydroxide. See, it's the intercalation of the hydroxide ion into the nickel oxalate framework. So you may think that the new compound is hydroxycarbonate, and when you discharge it, then hydroxide is gone and you able to retain nickel oxalate. So see, it's the framework remained stable, and that's why it will give the very stable performance. So to avoid the structure collapse, the framework, even from the oxalate or even bigger framework, can be utilized. However, we are finding that the this carboxylate framework is sufficient to give the stability to the electrode. So how the rotation ability of oxalate? Okay. So see, rotation ability of oxalate help in getting the three-dimensional structure. See, if oxalate will remain the planar, then you will get only two-dimensional structure or the 2D intercalation. But if it's really a three-dimensional structure, then diffusion can be much faster. So we don't have a very concrete proof currently for the this rotation or the three-dimensional network. But what we are getting is a very high diffusion. So there surely the more structural study with the help of the Raman or in situ Raman must be done to see this that and more exhaust studies are necessary to see the real structures, that they are that these metal oxalates are anhydrated metal oxalates are really getting three dimensional structure or not. But carboxylates are the more stable. Carboxylate is always a rotated carboxylate. So that's has already been established. So surely the controlling on these all the parameters are important, but see, I think these things depend more on your the processing or the heating rate. What is the rate of the hydroxide H2O removal is there in your compound. If you remove the water very fast, then the structure can collapse, and you may not able to get the C2O4 rotation. But if water will be slowly removed, then the removal of this hydrogen bonding may able to lead to the rotation of the oxalate framework, and you may get even with the pure oxalate three-dimensional structures. What is the suitable applied voltage for the solid polymer electrolyte? See, I'm not working on that one, but see, whatever the electrolyte you use, the voltage window depend on the oxidation potential. So suppose you have a C double bond C. So how carbon is going to oxidize to carbonates? That's the oxidizing voltage. So that's why EC, DEC, or ethylene dicarbonate and dioxalate have been utilized as a high voltage. So if you have a more of the single carbon, then the applied voltage will be always low. But a blend of the double bond and single bond into the solid polymer can help you to increase the voltage. And the scan rate is actually the rate of applying voltage. So, and when your conductivity is not very fast, then generally they give the residual potential over the material. So that's why you get a irregular degradation of your polymers. So these are the things in the general polymer chemistry. What is the advantage of graphite paper compared to copper and aluminum foil during the activated electrode for ADLC? See, graphite paper have the most advantage is that the interlayer structure. See, both carbon are having a same kind of electropotential. Whenever if you do the copper, then see current will be passed through the copper, then it will be transported to the electrode. So there is actually an interfacial potential involved when you do the metal electrode. So the sluggish performance is not because of this inactivity of activated carbon electrode, but actually it's because of the electron transfer from carbon to this one. However, when you do on the graphitic paper, then the sluggish performance may be due to the diffusion assisted, but that will be not due to the assist between the electron transfer. Head alter for household application. See, grid energy, what we are talking means the way we are actually transmitting the energy from our power plants to our houses. So if grid is stopped for even a few minutes, actually we are not able to use the energy. The energy is actually completely getting wasted. So the grid scale storage, what we are talking that when the grid will be off even for the few minutes or few seconds, that energy gets stored, not get wasted, so that it can be transmitted further. So there can be low line loss, and there will be a very low power cut. Even during the power cut, we can get the energy for few minutes, because the energy will be stored into the grid. So grid will keep on passing the energy even though they will not get from the energy from the source. So this is what we are talking when the world is talking when they are talking about the grid scale energy storage. The same component can be even utilized in the houses as a inverters. Okay. If we do not see any reversible peak in CV analysis world, a lie does mean that SPV have as a capacitor. If you're not getting a redox peak, then surely it's a surface dominant storage. So it's a more like a capacitor kind of behavior, not a battery kind of behavior. Battery kind of behavior, it means it must be the intercalative kind of behavior. So, uh, you must get a reversible peak whenever you are doing this one, especially for the lithium. If you are going to the battery kind of thing, so then only intercalative. But energy storage does not mean that it should be only a battery kind of or the intercalative kind of storage. You have to store the charge whatever the phenomena, it won't matter. See, if you have a more or the 50% or more domination of the surface storage and less than that of the intercalative type, then also you will not get a very better intercalative peak. You will get more like a more diffused or the broad peak. So that may happen, and most of the time that happens with the most of the anode material we work into the lithium ion battery section. Yes.
Very good afternoon, Dr. Singh. This is Dr. Shah from
Thanks.
NIT Rourkela.
Okay, thanks, sir.
I have a basic question. You mentioned about this cobalt oxalate hydrated compound as well as dehydrated cobalt oxalate
Yes.
as your supercapacitor. So, how is the dehydrated cobalt oxalate stable? Because you are using that 1 molar potassium hydroxide as an electrolyte.
Yes. So
does it have a
what we
tendency
have,
to hydrolyze?
no, that's what we have not found it. See, the performance is actually very stable, and that's why we have doubt that when we remove this water, because we do generally this very slow step of the, and it's actually coupled with the TGI experiment. So when we have seen that what are the phase transformation, so if you do that very slow water removal, so what we feel that this oxalate rotation is actually working, and we are getting a three-dimensional stable structure. So it actually intercalates the hydroxide, but it don't take water back into the structure. So then otherwise it will act like a water storage material rather than the electrocatalytic active material. So we are not getting this hydration of the cobalt oxalate back into the this anhydrated into the hydrated material. Hello, sir. Hello.
+4+3, that iron +4+3 and +3+2 redox couple in that oxide supercapacitor you mentioned,
Yes.
but actually there wasn't any peak. So how do you actually justify that reaction?
No, peaks are there. That's what I'm just going to show you. See, these peaks are there. If you can see this redox peak, like 0.85 volt minus and minus 0.59 volt. However, the surface domination is very high. So that's why you cannot distinguish it as a very distinctive peaks, but the peaks are there. So we have seen the redox peaks are there. Even if that has been visible into the charge discharge profile also. See, you are getting not a very continuous discharge. So even at these things, you can get actually a potential window. So the static voltage are there. It's not very continuous. But when your surface storage is more than 50%, then we will not able to get the complete redox voltage, redox performance, or the intercalative. So the redox peaks are there clearly. Even you can see into this plot. So these two peaks are there. So we are getting that redox peak. And when you have only LaFeO3, you will get only this iron 3 the peak dominated. So what we are suggesting is this iron 4.
Thank you so much, Dr. Pritam Singh, for an excellent talk. It was very informative discussion regarding challenges imposed for next generation storage devices, followed by intercalation of battery and ultra capacitor to get hybrid system for potential grid level application. Your talk must have surely motivated students and young researchers today. We have gained perspectives on advantages of metal oxide pseudocapacitors, charge storage mechanism, and many more. We really enjoyed your talk. Now, I kindly request Professor Pathasar to present the memento to Dr. Pritam Singh.
Thanks, sir.
So
Thanks.
on behalf of the organizing committee, we thank you for your nice presentation, and please
Thanks, sir.
accept the appreciation.
Yes,
We'll send it by. So this actually this frame actually depicting the the activities of the local tribal peoples, Rautela in the tribal belt.
Sure, sir.
Yes.
Thanks, sir. Namaste.
Thank you.
So one announcement from my side. Thanks, sir. So one announcement to dear students. See, I am actually organizing an international conference between 23 to 25th July here in IIT BHU. It's offline conference. So I welcome you all for the conference. Please join the conference, student and faculty. So I will send the invitation very soon. Please everyone join here in the conference here. This is also on the beyond lithium-ion batteries technology or the total energy domain, ranging from the fuel cells, batteries, capacitors, and other innovative energy solutions. So thank you very much. Thanks for inviting me for the talk. It was my pleasure to deliver the talk for such a wonderful audience. Thanks. Thank you very much.
Unfortunately, our invited speaker, Mr. Jubin Varghese, couldn't make it to deliver his talk today. So we'd like to conclude our session of 3 days national webinar on lithium-ion batteries and beyond. I would like to kindly request Professor Pathasar to deliver a vote of thanks.
So on behalf of the organizing committee, I thank you all for conducting this 3-day long webinar on lithium-ion batteries and beyond. It was a grand success. From the day 1 to day 3, there was many talks on different subjects, starting from lithium-ion batteries, then sodium-ion batteries. Also, we discussed about lithium sulfur and much more different subjects. So I would like to thank the organizing committee, especially the students, for whom this webinar could have been actually arranged. From day 1, when this webinar was conceptualized, and from the day 3, since the completion of this webinar, it would not have been possible without the active participation and help from our research scholar, as well as master's and bachelor students, BTech and MTech students. I particularly name them, like starting from Deepshikha Brahma, Siddharth Nanda, Mr. Uday Kumar, Ms. Tandarani Mohanta, Mr. Abhishek Kumar, Ms. Satya Shakti Das, Ms. Monica Singh, Ms. Ayushi. They have wholeheartedly put their effort to make it a grand success. I wish that in future we'll be able to arrange this type of webinar, and I hope that the legacy will continue. And in next year also, we'll be able to continue this on an annual basis. And if things moves in the right direction, we'll definitely go for offline mode instead of this online webinar. We're going to continue. We'll definitely do a 3-day long conference on lithium-ion batteries and beyond. So with this, I conclude our 3-day long webinar, and I call upon on stage, especially those students who are present here, including Professor Ranabroto Mojumdar, for a group photo. Thank you. Please, Abhishek, if you will come here, Ayushi can take the photo. Right, you can call. Yeah, you can be on the live. Yeah, fine. Yeah, it's okay. It's okay.
It's been online, like I can see us. Camera दिखने को नहीं आता है.
Come this side, brother. No. Chandra, come. Ayushi. सामने. Chandra, can we say Chandra?
Okay, okay, okay. किधर देख रहे हैं?
ठीक है, okay. Thank you.
Thank you. Thank you.
Thank you. Okay, broadcast center. And the
Thank you all.